One of the quintessential force equations, and we're going to get to this. This is actually Newton's second law. Okay, don't worry about it right now. But the idea is that the force exerted by an object or exerted on an object is going to be equal to that object's mass times its acceleration. Now, we know essentially what the units are here. Okay, what is mass always measured in? Kilograms. Okay, when we're talking physics, mass is always going to be measured in kilograms. So if you're given something in grams, you must convert it to kilograms. So the unit here is the kilogram. What is the unit for acceleration? Meters per second squared. Okay, we haven't given it a number yet. So if we're looking at meters per second squared, so if I multiply this, if I multiply out these units, I'm going to get force being equal to kilogram meter per second squared, right? That is what 1 Newton is actually equal to. All right, so when we're talking about newtons, all right, and when we're talking about weight, we learned this in grade 7 that, we had rounded it up to 10, where the coefficient of, or the gravitational force is 10 newtons per kilogram of mass, right? So in reality, what we're saying is the idea of a newton incorporates not only the acceleration of the object. What kind of acceleration do we normally see on this planet that causes these objects to stay on the surface of the planet? Gravitational acceleration, right? We remember that gravitational acceleration is 9.8 meters per second squared. And it's a positive number. Acceleration in the y, because we're giving it a direction, that's where the negative comes in. Okay? So when we talk about all this, when we're talking about all these forces, we're talking about forces in newtons. When we talk about the law of universal gravitation, we're talking about the idea that any two bodies with a set mass will be attracted towards one another. Case in point, you have a satellite or another planet or a moon, and you have, let's say you have the moon, you have Earth. Well, the moon has a mass, the Earth has a mass. Which one has the larger mass? The Earth. Now, the idea of the law of universal gravitation states that both of these objects are actually going to be attracted one towards the other. Even though the mass of the Earth is far greater than the mass of the moon will be actually attracting the Earth towards it, and the Earth will be attracting the moon towards it. Okay? The idea of this law of universal gravitation implies that you can figure out that force of that gravitational force between these two objects as long as you have their mass of both of them, the radius or the distance that separates them, okay, and something called the gravitational constant. You will be given the gravitational constant. All right? You will also be given this formula on this exam. It will not be in your June exam formula sheet, though. Okay? Now, if we look at this actual equation ends up being force of gravity is going to be equal to the gravitational constant times the mass 1, mass 2, all divided by the radius separating the two squared. By talking about the idea of the radius. Okay, so the radius is going to go, the vast majority of the time that you're going to see this type of problem is when you've got the Earth and you've got another celestial body away from the Earth. Okay? This type of formula is used where the idea of gravity on the Earth can't really answer that question. And what we end up doing is we end up going the radius from the center of the Earth, okay, to the actual center of the other object. That is the radius that we're actually looking for. Okay? Same can be said if, now this is almost a non-existent change, but if you've got a person on the surface of the Earth, you're going to basically go from the center of the Earth to the center of this person, and that's your radius. So this is why when we do that kind of problem, this actual equation becomes redundant. Okay, because if I'm 80 kilograms, well, that 80 kilograms is so inconsequential compared to the actual mass of the Earth. Okay, so we wouldn't necessarily use this formula for any object that is on the surface of the Earth. What formula do you think we'll actually use when something is on the surface of the Earth? Do you think we need to take into account the mass of the Earth? No, we don't. Okay, when something is on planet Earth, when it's on the surface of Earth and it's moving one way or another, and we want to know what the forces are that are interacting or that are affecting this object, are we going to care if we look at this? If we go Fg is equal to the gravitational constant, mass 1 times mass 2 times radius. Are we going to care about the radius of the planet? No, we're sure not. Are we going to care about the mass of the planet? Nope, we sure won't. What we end up caring about, though, is the idea of gravity. Okay, and if you look in your notes, it explains, it actually works this formula out, all right, with the mass of the Earth, with the gravitational constant, with the radius of the Earth, and what you end up being left with is the idea of 9.8 meters per second squared being your gravitational, being your, that's where that gravitational acceleration comes from. Okay? We're not going to use a lot of this stuff when we're looking at objects and the forces acting on them on Earth. What we're going to use instead is the force of gravity is going to be equal to the object's mass times gravitational acceleration. All right? Now, you're going to be learning about a lot of different types of forces here, and these small little subscripts are going to become very important. They identify what force you're describing. Okay? So in this case, if we've got mass in kilograms and we've got gravitational acceleration in meters per second squared, this is where we get our newtons. If we look at example 1 on page 7 of your notes, it says calculate the gravitational force exerted by the Earth on a 75 kilogram person. So if we write down our givens and we write down our formula, we'll get the following. So if we look at our data, we see that Fg has a vector sign. Vectors imply that it's going to have a magnitude and a direction. So when we're doing the math, Fg is equal to m times g. We end up with 75 kilograms times 9.8 meters per second squared. And we end up with 735 newtons. That is the magnitude. That's the length of our arrow. Now, the answer says 735 newtons downward. Because where is the force of gravity pointing? It is pointing you towards the surface of the Earth. So this is your magnitude. Downward is your direction for your vector. Okay, another way of writing this is, and I mean, this is where the acceleration in the y comes in because we associate the direction with it. Had we actually plugged in negative 9.8 meters per second squared, we would have come up with a negative 735. What you can say is you can show the math coming up as just a number, and then answer Fg is equal to negative 735 newtons. Negative implies that it's downwards. It's opposite of positive motion. It's a negative y. Okay?